Okay, so whenever there's a spark, notice that the spark happens only at a given distance. It's charging up his body, obviously through friction, and then the spark is going to happen only, look at this distance, this is about an inch, and sometimes it's less than an inch. So the question is this, why does the distance matter when it comes to spark? Okay, so we know from Franklin that spark is the same as lightning, right? All right, so we know that the spark and the lightning is the same thing. And then when it comes to spark or lightning, notice that the distance matters. So the spark is only going to happen within a certain distance. Okay, so it's about an inch, maybe less than an inch. Why not like 5 feet? Okay, so what determines the proximity between two opposite charge regions in terms of the spark occurring? Okay, so again, it's the same question. Notice that it's a cute little picture. She's got a nice little smile. Look at the hair is rising up. And then her brother thought that this was funny, so he snapped a picture, and then they left. And shortly after they left, lightning struck. One person died. A number of people got injured. High ground versus the low ground. Which one is more likely to be struck by lightning? You know the answer, right? The high ground. Again, the question is why. And you will immediately, from that little spark demonstration that the distance matters, right? Closer the opposite charge regions to each other, more likely that there's going to be a spark, or in this case, the lightning. But the problem is not so much that our build on common sense is right or wrong, that logic doesn't work 100% of the time. Why not? If high ground is more likely to be struck by lightning, why is it that the tallest structures in cities are not the ones that get struck by lightning 100% of the time? Why is it that the high ground is not the one that gets struck by lightning 100% of the time?
In Glenview, high winds took down a power line, trapping a woman inside her car.
Also, the question of women being inside a car. Notice that you got the live wire touching the metal casing of the car. This car is electrified. Now you know why she's safe as long as she's on the inside. She's going to be safe as long as she remains on the inside, as long as she's not stepping outside. Let's put it that way. Because the net charge is going to be distributed outside of metal. Net charge cannot penetrate into the metal. Metal is a conductor, so the light charges, the net charge is going to repel to the surface immediately. So she can touch the metal on the inside. We'll get that. So she can touch the metal on the inside, she's going to be fine. We had a big discussion about it. But she can also touch the metal outside, she's still going to be fine. So the question is why? It doesn't make sense because the electricity, the current, the net charge is going to be outside. This car is electrified. All right, this is part of the live wire that you're looking at. Why is it that she's able to touch the outside of the vehicle, and yet she's still fine? What's going on there? So we will definitely have an answer for that one. So that's the main investigation, the next phase of our investigation. All right, so then everything that we will discuss is going to be related to the electrical potential energy and electrical potential and potential energy. Okay, so how are they the same or how are they different? Okay, so which means that we have to go back to physics 1 and then revisit a concept of the work energy theorem. That's what we'll do. Okay, so this is meant to be a quick review, so we'll do just go over the concept. Okay, so remember the concept of energy. I said it's an abstract concept. The concept is so abstract that Newton was dancing around it, but he did not discover it. It was discovered during the 19th century, during the Industrial Revolution. And immediately, the engineers and physicists noticed that there was an underlying concept that just appeared within the mathematics. So that's called energy. So there's something about energy that
began according to plan as they leapt off the bridge while tethered to the cable.
Stand up. On 3 going. On 3 double. That's right. 1, 2, 3, go.
But as the team was about to reach the end of their first arc, the cable snapped. And 4 men and 1 woman plummeted 70 feet at 80 miles per hour, slamming into the water with terrifying force.
Okay, I'm on the outside, helmet cam. Kenny, myself, boy, Sarge. She does the front flip. Here we come, going in full velocity right here. Probably reach about 78 miles an hour, right about here, 78 miles an hour. You'll see the harness disconnect from the cable right there. The seat just disconnect, my arm goes out, and here we come to the water. Pow! Oh, took a ton of bricks. So look at the splash, like 40 feet. Quick at action now.
Okay, so a couple of things. Those of you guys who've taken physics 1 with me, you guys have seen this like 1,000 times. Okay, so they're going 78 miles per hour in this direction. Okay, so how do we know that? We'll find out. And then the harness snaps, it gets disconnected. They'll hit the water at 91 miles per hour. Okay, so question number 1, how do we know that they were going to be going at 78 miles per hour? Now, the second question is, how do I know that they will hit the water at 91 miles per hour? Okay, so all 5 will survive this at 91 miles per hour. So what would have happened, instead of doing the pendulum move, what if these people were to just jump directly from the bridge for a distance of 20 to 70 feet? Would they still have survived? Do you think they would be going faster or slower, about the same speed? All right, so those of you guys who've taken physics 1 with me, that you already know the answer. Those of you guys who've taken physics 1 somewhere else, obviously more than likely you have no idea what that. Okay, so definition of energy is capacity to do work. So if you have energy, you should be able to do work with it. So the question is, what is work? something, it's a process of transferring energy. All right, so when you do work, you transfer energy. So the definition of energy is capacity to do work. So it gives you the ability or the capacity to do work. And what happens when you do work is that energy is going to get transferred. Well, work is something that happens when there's force causing displacement. Or notice that there's force causing displacement. So the car is getting displaced under the influence of this force. So the force influencing motion or causing displacement is known as work in this case. So what happens when you apply a force on something and cause it to get displaced, which means that you transfer energy to the object. So the capacity to be able to apply a force on something and make it move is known as energy. So the energy gives you the capacity to generate a force that could generate motion and energy. So the proper unit is going to be J. J stands for joules. So mathematically, this is known as the work energy theorem. All right, so here's the mass. You apply a force on it. As a result, it gets displaced along the x direction. So force times displacement, x is the same as r in this case, is known as work. So the displacement could be along the x, y, z directions or anything in between. Some books will say d or s. They mean the same thing. All right. Force causing displacement is your work. All right. So what happens when you do work? You transfer energy, right? All right. So when the work is done, the energy gets transferred. In the United States, we use calories. United States calories are 1,000 calories in physics. All right. So this was a fast review of the meaning of work. All right. So there's force. No displacement, crate's not moving, no work is being done, which means that no energy is being transferred. There's applied force acting on this guy. It gets displaced along the direction of the force, which means that the work is being done, which means that the energy is being transferred to him. All right, so speaking of work, for work to exist, the force causing displacement has to have a component along the direction of motion, which means that this force has to be responsible for the work itself. Okay. So obviously there's force, displacement in this direction. The force is at an angle, so which means that this force has a component along the direction of motion. What that means is this force is responsible for this motion. So work is being done. All right, so speaking of work being done, all right, so the force is coming at an angle. Displacement is along the horizontal direction. This is the angle at which the force is applied. So the component of the force, which is going to be parallel to the displacement, is the component which is going to be responsible for work. All right, so whenever you do work, the work represents the amount of energy gets transferred. Okay, delta E is the change in energy. So the work is a process of transferring energy, which means that the energy is being transferred. Okay, you can transfer energy into a system or out of a system. All right, so the energy can be transferred to the system or from a system. That's what it means. Okay, so it depends on the work. All right, so let's just go over the basics. Positive times positive is positive. Positive times negative is negative. Negative times positive is negative. Negative times negative is positive. So displacement is a vector to the right positive, to the left negative. Up is positive, down is negative. Forces are vectors to the right positive, left is negative, up is positive, and down is negative. Okay, so this is going to give us positive and it's going to give us positive work, negative work, and no work. So let's go over the basic definitions. All right, so in all three cases, the objects will get displaced in the forward direction. Force is in the direction of displacement. Force is opposing displacement. Force is 90 degrees to displacement. Okay, force is contributing to motion here. Okay, so force and displacement are positive. They're in the same direction, so it's going to give us positive work. When the work is positive, energy is gained. So it's going to give you a positive gain of energy. So which means that the energy gets transferred to the object. So the force is contributing to motion. It's in the same direction. Force is responsible for this displacement. Okay, so which means that the object gains energy. So positive work means that the energy is gained. All right, so in this case, displacement is in the forward direction. The force is opposing motion. When the force is opposing motion, what's going to happen is this force is negative, displacement is positive. Positive times negative is going to be negative. So it's going to give us negative work, which means that there's going to be a loss of energy. All right, so here the energy is gained, here the energy is lost. So which means that this mass is losing energy. So when the work is negative, mass loses energy. That's what it means. All right, so the last case, once again, the displacement is forward, so the motion is forward, except the force is in the opposite direction. Now, this force does not have a component on the direction of motion. All right, so it does not really contribute to motion. This force has nothing to do with this motion. So no work is being done, no energy is being transferred. All right, so force and displacement, same direction, energy is gained, positive work. Force opposing motion, energy is lost because the work is negative. Force not having a component along the direction of motion, no energy is being transferred. All right, so lifting something up, the work is positive because force and displacement are in the same direction. So the energy gets transferred to the cat. So positive work done, energy is gained. All right, so moving a cat forward at a constant speed, the force is 90 degrees to motion. Force is there to balance the weight. No energy is being transferred because the no energy is being done. All right, so placing a cat back on the ground, force is there to balance the weight. Displacement is in the downward direction. So apply force in the opposite direction. Displacement is in the downward direction. Work done is negative. So which means that the cat is losing energy. That's what it means. So which means that the energy is being taken away from the cat. All right, so force of gravity extends all the way out to the moon. So the question is, how much energy gets transferred to the moon by the force of gravity? How much work is being done on the moon? All right, so the motion is, notice that it's tangential motion, meaning that the motion is going to be pointing in the direction of the curve. It's going to be 90 degrees to the force of gravity, which means that this force doesn't really contribute to motion. So no work is being done by it. No energy is being transferred to the moon by the force of gravity. Mathematically, we have to focus on this one because trick is going to be required. All right, so this is a generalized statement for work. So force, this is the component of the force in the direction of r. So this is cosine of the angle. So it's going to cause a change in energy, right? All right, so angle is 0 degrees, which means that the force and displacement are in the same direction. So the cosine of 0 is going to be 1. All right, so which means that force and displacement are in the same direction. All right, so which means that the energy is going to be gained. So that's the interpretation of the formula. If the force is pointing in the opposite direction, the angle is going to be 180 degrees. Cosine of 180 degrees is going to be -1. So it's going to give us negative work because that thing is negative. So energy is being lost. If force is 90 degrees to motion, cosine of 90 is going to be 0. So no work is being done. So this formula is a nice little summary statement for this case. It is a nice summary statement. All right, so what do we know? So whenever we do work, we transfer energy, right? So the work is the amount of energy that gets transferred. All right. Whenever you lift something, obviously you're doing positive work on it. So there's force in the opposite direction. Displacement is in the same direction, which means that whatever it is that you're lifting, you're transferring energy to it. All right, so whenever you lift something up, by the amount of work that you do against gravity by lifting it up, it's going to get transferred to the object that you're lifting. It's going to get stored in that object. The energy that you transfer becomes stored in that object. So the stored energy is known as potential energy. Or gravitational energy. So I'm going to be lifting something up. All right, so I'm doing work against gravity. So gravity is what provides the gravitational force acting on this, which becomes the weight. So I'm lifting it up along this direction, along the vertical direction. It gets displaced along the vertical direction. The letter Y represents the displacement along the Y direction. So I apply a force, this is your displacement. All right, so the force times displacement represents the amount of work that I do. So the work that you do is the amount of energy that you transfer. So the energy gets transferred in the form of potential energy. So delta P represents the potential energy. All right, so the potential energy, it depends on the mass of the object that you're lifting. It's going to depend on the gravitational acceleration. Mg also represents the weight. So this represents the weight that gets displaced in the upward direction. Believe it or not, guys, things will have weight. That's the amount of gravitational force acting on. So you have to do work against gravity to lift something up. The amount of work that you do is the amount of energy that you transfer. So that's the amount of energy that gets transferred to the mass that you're lifting. So that's the potential energy. So how do you store energy in an object? You store energy in an object by lifting it up against gravity, by doing work against gravity. So the gravitational potential energy is the amount of energy that the object has by virtue of its position in a conservative force field. Whatever that is, it's going to make sense shortly. So it's mg times 1. Higher up you go, the larger the potential energy is. The second form of energy that we discussed was the kinetic energy. That's the energy in motion. It's related to speed. Notice that this car is speeding up, going from 20 meters per second to 30, right, in the forward direction. It's accelerating, which means that there's a force acting on it. And notice that the force is along the direction of displacement. So the force is in the forward direction, so it's displacement, so which means that the work is positive. So which means that the energy is being transferred to the object itself in the form of motion. So that becomes kinetic energy in motion. So kinetic energy is related to motion. So here's mass moving at a given speed. Because it's got speed, it's got energy. The energy that it's got is known as kinetic energy. All right, so take speed squared, multiplied by the mass, divided by 2. So that becomes the generic mathematical expression for kinetic energy. So it's the energy in motion. All right, so the amount of work done is going to go into the kinetic energy of the car. Right, so mechanical energy is a combination of kinetic and potential energies. So kinetic plus potential is going to give you mechanical energy. So combination, the total of kinetic and potential energies. Sum of kinetic and potential energies is known as mechanical energy. So capital E represents mechanical energy in this case. Conservation of mechanical energy means the constancy of mechanical energy. So this sum is going to remain constant. All right, so constancy means conservation. So constant means it's conserved. So mechanical energy is conserved. So what that means is if potential energy goes down, kinetic energy is going to go up because mechanical energy is constant. All right, if kinetic energy goes down, potential energy is going to go up because mechanical energy is constant. All right, so that's point. If there is a conservative mechanical energy is constant, kinetic energy gets converted into potential energy gets converted into kinetic energy. All right, so these two types of energies will get converted to each other. All right, so gravity is the only force acting in this case. So notice that as soon as I drop the ball, it's got potential energy goes down, right? As the distance goes down. So notice that it speeds up, so kinetic energy goes up. So as the height goes down, the speed goes up. So which means that potential energy turns into kinetic energy. When I throw this up against gravity, what happens is as the height goes up, the kinetic energy goes down. which means that potential energy goes up, the kinetic energy goes down. So which means that kinetic energy turns into potential energy. So I provide a bit of a speed in the forward direction. As the speed goes down, the height goes up. All right, so this is known as the conservation of mechanical energy, meaning that the mechanical energy doesn't change. Potential energy goes down, and speed goes up. Potential energy height goes down, the speed goes up. Potential energy goes down, kinetic energy goes up. Okay, and then when you throw it in the opposite direction, kinetic energy turns into potential energy, and potential energy turns back into kinetic energy. All right, so the next question is, what conserves mechanical energy? What conserves mechanical energy is a conservative force. Okay, so what's a conservative force? Guys, conservative force is any force that conserves mechanical energy. Any force that conserves mechanical energy is known as a conservative force. Example of a conservative force is, notice that I lift this up. I'm doing work against gravity. As soon as I let it go, what happens? Gravity takes over. What does gravity do? Gravity takes that potential energy and converts it into kinetic energy. All right, so gravity is a conservative force. Work done against gravity is going to become stored in this object as potential energy. As soon as gravity takes over, potential energy is going to turn into kinetic energy. When I throw the ball in the upward direction, once again, gravity takes over, it takes the kinetic energy and turns into potential energy. So any force that conserves mechanical energy is known as a conservative force. The example, I think we've seen two of them last semester. One of them is gravity, and the second one is the restoring force. All right, so restoring force and gravity. Okay, so we will see a bunch of other examples this semester, so that's the reason why I have to review that. Okay, so when the only force acting is gravity, what happens? That potential energy that comes from initial height is going to turn into kinetic energy by the time it reaches the ground, right? All that potential is converted into kinetic. All that potential turns into kinetic. Okay, so I'm making calculations simpler. All right, so
Stand up. The group is ready for the jump that will change their lives forever.
On 3.
1, 2, 3, go!
On 3.
1.
just a refresher. It should be 78 miles per hour here. And it should be 91 miles per hour there. All right, so how do you get those numbers? Okay, so there are a bunch of assumptions that we're making. So it's a pendulum move, number one. Initial speed is going to be 0. So the question is, how fast will they be moving at the bottom of the arc, right? All right, so I usually measure my distances with respect to the lowest point in motion. Lowest point in motion in this case is going to be at the bottom of the arc, which you're looking at the pendulum move. So I'm going to take that height to be 0. And then I'll measure the initial height with respect to it. So initial height is going to be, that's the length of the cable. So it's length of the cable that these guys were using was 200 feet. All right, that's it. All right, so figure out the speed. So we should get 78 miles per hour if the calculations are correct. All right, ignoring air friction, the only force acting is gravity. Gravity is the only force acting. Mechanical energy is conserved. So mechanical energy is going to be conserved. So here's your initial mechanical energy. Here's your final mechanical energy. So conservation of mechanical energy means these two values will be equal to each other. All right, so I finish up my conversions to the metric units. All right, so mechanical energy is going to be constant. So here's your final mechanical energy. This should be E sub 0. So that's your initial mechanical energy. You know the final height is going to be 0. So this term goes to 0. You know initial speed is going to be 0. So that term goes to 0. And then solve for V. It gives you the speed. Immediately you know that the speed only depends on the initial height, measured with respect to the lowest point in motion. All right, so plug the numbers in. And it should give us 78 miles per hour. All right, so that was straightforward.
Stand up. The group is ready. 5.
So that was 78 miles per hour, and then hit the water. So the next question is how fast. Okay, let me check to see. All right, now I want to know how fast. So it should be 91 miles per hour. So how do we do that? Once again, I'll do the same thing that I did before. Lowest point in motion, I'm going to take that to be 0. The initial height, I'm going to measure with respect to lowest point in motion. So the initial height is going to be the distance to the bridge, so it's going to be 270 feet. So 70 feet drop after the cable snaps, or the harness gets disconnected. And then you have 200 feet of cable, so it's going to be 270. Once again, the motion is occurring under the influence of gravity as soon as they jump. All right, so what's the final speed? All right, so once again, you do the conversions. Gravity is the only force. Gravity's mechanical energy is conserved. So initial and final mechanical energies are the same. So here's the mechanical energy formula, conservation of mechanical energy formula. So it's the same algebra. So which means the final speed only depends on the initial height. Boom, boom, boom. So plug the numbers in. There should be about 91 miles per hour. Okay, so that worked out. So the next question is, what if these people decide to jump directly into water? Okay, how fast would they be moving? Guys, again, news for you. When you do the computations, once again, mechanical energy is going to be conserved because gravity is the only force acting. Initial height is going to measure with respect to the final height. Final height is going to be taken to be 0. All right. So which means that our mathematics is going to look exactly the same. We will get to use the same formulas exactly the same way. So which means that we will end up getting the same number. This time you will also get 91 miles per hour. Okay, so what do we learn from this? Which means that if there's a conservative force acting, path of motion doesn't matter. Okay, so this one is going to take a little bit longer. This one is going to take a little bit shorter. So if you want to do sightseeing, this is the way to go. If you're in a hurry, this is the way to go. So path of motion is not going to happen. It's not going to matter. All right. So all that potential energy is going to turn into kinetic at the end. Okay, some of you guys kind of get confused because you're thinking, wait a minute, there's an extra force acting here. Yeah, there's tension acting on it, but tension is always going to be 90 degrees to motion itself. So the tension does not contribute to motion. All right. So which means that it does not add energy to the system. It does not take energy away from the system. All right. So when this thing is moving in this direction, the tension is going to be 90 degrees to it. So which means that it's still happening under the influence of gravity and gravity only. Okay, so the only thing that the tension does, because it's acting on the system, it causes this delay. All right, so this is going to take a little bit longer, but the end result is still the same. Okay, so this is one of the things, the key things that I want you to remember. This is one of the biggest discoveries in physics, the inventions or discoveries, the concept of energy, the conservation of mechanical energy. It makes life so much easier. It's going to make life so much easier in terms of figuring things out. All right, so we're done with this. Moving forward. All right, so if the mechanical energy is conserved, path of motion doesn't matter. Just remember that. Okay. Case in point, same ball thrown from the same height with identical initial speeds at different angles. Which one, if any, will be moving fastest at the time of impact? Which one is going to have the largest impact speed? Remember, guys, path of motion doesn't matter, right? All of them will have the same impact speed. All of them have the same. In all three cases, the ball is the same potential energy. In all three cases, it's got the same initial kinetic energy. So initial potential and kinetic energies are the same. So it's got the same initial mechanical energy. Gravity is the only force acting. It's going to have the same final mechanical energy. So all that mechanical energy turns into kinetic at the time of impact. So they will all have the same speed. All right, so all objects projected from identical heights with identical initial speeds will reach the ground with identical mechanical energy concept. All right, so let's talk about electric potential energy. All right, moving forward.
Bob and I are here to tell you about something that has us very excited. NEC's Parabola range of televisions. They've got a 3-year warranty, which we think is fantastic. They come from the same people who have sold over 1 million Australian-made colour televisions. Superb sound comes from the surround sound speaker system, but
all right, so it's from Australia. Obviously, they're trying to sell TVs, high-definition TVs. Okay, so the quality of commercial up to this point is not very interesting. Out of a 10-point scale, I would give it a 1. And I mean, obviously, you don't want to go out and get a TV and then watch these people trying to sell you a TV, right? So it's not that interesting. In the United States, the commercials are a lot more exciting. So that probably makes life a lot more exciting and interesting in the United States compared to Australia.
Best feature of NEC's Parabola is its lifelike picture.
Ooh, it's called a misdirection. The quality of this commercial went from 1 to 10 immediately. You guys didn't realize that the guy in the background was on TV. So that's the quality of picture. The quality of picture is such that it's actually just as good, if not better, than real life. That's called high definition.
Bob and I are here to tell you about something that
has acting is phenomenal. This guy's going to be as boring as possible. He's going to look as bored as possible, and you really can't tell.
NEC's Parabola range of televisions. They've got a 3-year warranty, which we think is fantastic. They come from the same people who have sold over 1 million Australian-made colour televisions. Superb sound comes from the surround sound speaker system, but the best feature of NEC's Parabola is its lifelike picture.
Okay, so we'll have to talk about TVs briefly, and then high-definition TVs, because there are a couple of things that we'll have to grab.
Bob and I on television sound.
Okay, guys, high-definition TVs today, it's commonplace, not a big deal. All right, so came to Chicago in 1996 from Virginia. I was working on my PhD in nuclear physics at the time. All right, so I was working on my dissertation. So I came to Chicago. I'm thinking, I was kind of bored working on it. So I had 2 more years to go to finish it up. And I kind of enjoyed teaching. So I was lucky enough to get a job at an art school. So they said, can you teach physics to art students? Make it visual, make it interesting, just go easy on the math. And, being inexperienced, you think that this is an easy thing to do, only to realize that that was a horrible decision. Okay, number one, you try to make stuff visual, which means that I had to get myself cables, start recording these shows. Back then they had VCR recorders and 6-hour videotapes. If you don't know what I'm talking about, talk to your parents about it. So I could record 6 hours at a time, and I didn't have enough time to watch them. So I would just watch this stuff about an hour a day. And then you got a 6-hour tape. It would take about a week to actually go through it. if you're lucky, the TV was just so horrendously bad when it came to science at the time. You could get like 30 seconds of material that you could use per lecture. It was such a monumental waste of time. So I would come up with these ideas. I'm trying to edit stuff. It took, I was literally working 60, 70 hours a week preparing these lectures, and you guys are benefiting from that, obviously. Right? These PowerPoints go back almost 20 years, guys. Anyway, so except that for these lectures were god awful. I couldn't come up with decent lectures. Visuals were not good enough. Technology wasn't here, and then I was just swimming in crap, basically wasting my time. And I started to run out of time because I didn't have enough time to work on my PhD dissertation. I was just spending a lot of time just doing this sort of stuff. And I was making about $30,000 a year and working, God knows, about like 60, 70, 80 hours a week, just working on these lectures. And eventually I got burned out. All right. These lectures started to take shape 3 or 4 years after this because there was a lot of trial and error trying to figure out how best to relate to students. So whatever works with art students, evidently works with everyone else. All right? So if you're understanding physics, you have to thank art students for that. Okay. This style was developed at the art school. Except it got to a point, I figured that, yeah, I was just wasting time. It didn't feel like it was going to work out. So started to look around and thinking I should just get a full-time job somewhere, work 40 hours a week. At least at night, I could work on my PhD dissertation. All right, it would just give me enough time to actually get my life together, pull my life together. All right, so that was the whole idea. Anyway, so started looking for a job. And at the time, there was a famous company located in Chicago, TV company, Zenith. You probably never heard of it. So Zenith was like, it was as big as Microsoft at the time, and they used to build TVs and the computer monitors and all that stuff. So they were interested. They were looking for a physicist, evidently. So I sent in my resume. They were interested. So we set up the interview. So the first person I remember that I had to talk to was the HR, human resources. So I went in there, and then so we started talking, and then so they wanted to know what the salary was at some point during the interview process, and then she said, "Well, it's like $120,000 a year." I'm thinking, oh, gee, this is awesome. So what is it that I need to do for it? Because that's like 3 times the money, or 4 times the money that I was making at the time. All right, just imagine that. So you're going to be working 40 hours a week and make $120,000 a year. That's your starting salary. She said, well, just go to the physics department, and then they will just explain it to you, because my interview was at the physics department. So I went to the physics department. So there's a little table. There's one guy sitting there. The guy looked like he was in his 50s. And so I sat across from him. And then we started chatting a little bit, and then he asked me a few questions. And so one of the questions that he asked, he said, what do you know about HD TV? Because that's the sort of research that they were working on, and they needed a physicist for that. Okay, so at the time, guys, there was no HD TV in the market. Okay, I knew TV was television. I didn't know what HD stand for. He said, oh, it's high definition TV. I said, what does it mean? He said, it's high definition TV is like a regular TV, except the image quality is such that it's lifelike, if not better than life. Okay, I thought he was kidding at the time. But in reality, guys, if you have a really high quality HD TV, all right, just go near the screen during a football game. Obviously, the Super Bowl is coming up. Check to see if you can see the grass on the field. All right, the definition is almost lifelike. It's probably better than lifelike because it's digital. You can see details. It captures the details in such a way that it's it's pretty darn good. I'm thinking, oh, this is awesome. So his next question is, do you know how a TV works? I said, yeah, well, just give me a remote. I'll show you how that works. I say, yeah, of course I do. Because I also worked on, for my master's, I was working in electrical engineering. So I figured that I could actually build a TV if I had to on my own. I said, no, we don't need you as an engineer. We need you as a physicist. He said, we have a huge problem that we're trying to solve. I said, okay, so what's the problem? Evidently, they made these prototypes, HD TV prototypes, 4 years earlier. And then when the prototype had a slight problem, it would generate a spark within the TV. It would be functional for about 6 months at a time. And within that time period, there would be a spark within the TV somewhere. And then it would just fry the electronics. Then he started explaining. I said, okay, so explain more. He said, so within the TV, you have to generate an electron beam. Okay, technology has changed quite a bit. It's not the same anymore. Okay, this is the initial, these are known as cathode ray tube TVs, the initial TVs 20 years ago. All right, so you would have an oppositely charged regions inside the TV, just like that. So one region, you got a plate here, it's going to be negatively charged. The other plate would be positively charged. All right, so this is the setup that we will get to use quite a bit for the next couple of weeks. Okay, this week's lecture is about this setup. All right, so you would have a little filament here, metal filament, and you would just heat it up. So what happens when it's heated, this is metal, so you got free electrons moving around, right? So you could ionize the metal. So which means that it's going to give up its electrons. And notice that there's a very strong electric field region here. So electric field is going up. All right, so there's going to be an electric field in the upward direction. So you would generate this electron beam, and there's a hole, the opening at the center. Okay, this is a two-dimensional representation of it. And by using magnets, electromagnets, you can trace the electron beam onto the screen a couple hundred times per second if it's a regular TV, a few thousand times per second if it's high definition. Okay, so that's it. So you generate an electron beam by heating up the filament. So it's just going to give up its electrons. And there's a strong electric field. The electric field acting on these electrons will induce a force on them in the opposite direction. So these charges will accelerate in the downward direction into this opening, a hole. And then they will go through the hole, and there's a strong magnetic field region. So using electromagnets, you just trace the beam onto the screen a couple of hundred times per second. Okay, so this is known as a capacitor. Engineers call this the electron gun because they're cowboys, right? Because you're able to shoot electrons out of the hole. That's what it means. Okay, the problem, he said, is this will work just fine, except it will work for 6 months at a time, almost. Within that time period, it would just generate a spark, and then it would just zap the electrons. I said, okay, so I said, what do you want me to do about it? He said, fix it. I'm thinking, all right, I had some ingenious ideas, 3 theories immediately. It was explaining it. The reason why I have theories about it is because this is the same as lightning. Okay, I was already teaching this at the art school. As soon as this guy mentioned it, I figured that I have the answers. Okay, so as I was about to say something, immediately I noticed that I don't have the job as yet. So just ask questions and listen. I said, my first question is, so you guys had this problem for the past 4 years, right? He said, yes. I said, so how many people are working on it? He said, me and the other guy. I said, how many people are working in the physics department? He said, just me. I said, are you a physicist? He said, no, I'm an engineer, electrical engineer. I kind of knew from the way he was describing it. I said, how about the other guy who was working on it with you? He said, oh, the other guy was a physicist. He had a master's degree in physics. I said, okay, so what happened to him? He said, well, you know, they worked together for about 2 years, and then 2 more years. Eventually, the guy decided to quit and get his PhD in statistics. I'm thinking, this is weird. I wonder what happened, because 4 years is way too long. Companies would not spend that much money 4 years. This problem should have been solved 4 years ago. I said, so what do you guys do? The first 2 years, they came up with 3, 4, 5, 6 different methods. And they tried the 3 things that I was thinking immediately. None of that worked. Okay, so that was the 3 obvious things. Whatever they were, they didn't work. And then they came up with these real ingenious methods the first 2 years. None of that stuff worked. Okay, all of a sudden I'm thinking, oh, wait a minute, these people kind of exhausted all the physics. So maybe it's not even physics related. I figured that this is probably related to material science. And material science was something which was a bludgeoning field, burgeoning field, not bludgeoning. All right, it's a field that falls between chemistry and physics. It's known as material science today. I knew one person working at NASA, and that person was specializing into it. And so I knew at that point that this was more of a material science problem than a physics problem, but I didn't want to say anything right away. I said, okay, so first 2 years, they tried this and that, none of that stuff worked. And then I said, then what? And then they started applying these advanced statistical methods to this problem. I remember kind of vaguely just rolling my eyes, because this doesn't have anything to do with advanced statistical methods. That's the sort of stuff I used to do at Fermilab, so it's nothing to do with it. I said, who came up with that idea? He said, the physicist did. I'm thinking, okay, so that's weird. So I said, and then what happened? He said, nothing. And so they spend a year applying these advanced statistical methods, and then what? And then another year applying even more advanced statistical methods. Once again, nothing, which I kind of knew. And then I said, then what happened? And it said that this guy became so good at statistics, he quit and decided to get his PhD. I'm thinking, oh, I know what this guy's up to at that point, because I'm thinking I could probably do the same. I mean, he knew at that point, 2 years earlier, that this has nothing to do with physics. He needed a job. He's probably making $250,000 a year or something, or close to $200,000 a year. And no one understands physics, including the engineer, obviously. It's just coming up with these methods and trying to learn as much about statistics as possible and quit and move on. So I'm thinking, you know, should I fake it? All right, you can fake it. It's not like a big deal. But even if you try to fake it, these guys kind of did anything and everything possible using physics, so there's nothing else left. And besides, the company's not going to, they're not going to invest more into this at this point. 4 years is a long time. All right, unless you come up with results, it's not going to work. At this point, I know it's probably material science. I wanted to make that suggestion, but at the same time, I want to keep my options open. So I said, what else do you guys have? He said, that's it. I said, so what happens after we solve this one? He said, well, we'll find you something else. There's not going to be something else. This is the only problem that they have at that point. So I'm thinking, at that point, I said, it's not really worth the risk at this point, because you can't solve this problem using physics. You don't want to cheat a company out of $250,000. It's not really worth it either. I said, I have to think about it. I didn't want to make a decision. I said, I have to think about it. At that point, it's a bit of a reversal process. The guy goes, he said, yeah, but you can publish this, right? In high voltage magazines. I said, I know this is beneath you, a nuclear physicist, and you can publish it and you can make a name for yourself. I said, yeah, I have to think about it. He said, is it because of the money? We can pay you more. I'm thinking, let's not push it. I said, I have to think about it. All right, so I thought about it. I said, it's not worth it. The company is going to pull the plug anyway at this point. So I called up the HR a couple of days later, explained the situation. I said, as far as I'm concerned, as far as physics is concerned, this is it. I mean, I came up with 3 things. These people came up with 20 different things. They tried this and that, nothing worked. I said, more than likely, it's a material science thing. I explained what material science was. And I said, you guys have to come up with metals they can hold on to their electrons. Okay, it's modern physics is known as a work function at extremely high voltages, whatever voltage is. So that's what we're going to be discussing. So I just made my point. I said, my suggestion is forget physics, just get a material scientist. That's it. Anyway, so about a week later, I get a call back from Human Resources. They thanked me for my recommendations. It wasn't a recommendation. I was just making some suggestions more like it. And then they said they shut down the physics department upon my recommendations. So they end up moving these operations to Korea. And that's it. Okay, so that kind of made sense because I think it was cheaper. Because, hey guys, this is basic physics or material science. You don't need to have expensive people working in the United States. They figured that it was cheaper to have it done in Korea. And I don't know what happened. Zenith was the only company that was not able to solve this problem. Every single company was able to solve it. Zenith eventually solved the problem, but they entered into the market 2 years later than they should have as a result. And they end up losing their dominance in the United States. I'm not sure if this company still exists. All right, so instead, I end up going back to the art school. And that's what happened. Okay, so the reason why I'm talking about this is because of this minute lightning that you're dealing with. All right, so spark. How did I know that this problem that they were trying to solve was not physics related, 100%, or at least you could not solve this problem using currently available physics? All right, because the problem that they were trying to solve is exactly the same sort of problem that we still try to solve with lightning. This is 100% identical to lightning. And also, he was talking about high voltage magazines. All right, so what's voltage? What's potential? All right, so that's what we will discuss. All right, this was a long story, but it's related. All right, this is 7:38. Just take a break for 10. Be back by 10:02. Okay, so let's move forward. Okay, so electric potential and electric potential energy. Okay, so let's talk about electric potential energy just briefly. Come on. Okay, so positive charge, positive charge. Okay, so try to bring this positive charge near this one. What do you think is going to happen? It's going to experience a lot of repulsion, right? Light charges repel. So the closer you try to bring the positive charge to the other positive charge, the more work you have to do. Okay, so what happens to the amount of work that you do in bringing a positive charge near another positive charge? The work that you do is going to go into the potential energy of the charge. Okay, remember when you lift something up, the amount of work done against gravity will become stored in that object as its potential energy. The same thing happens to these charges. The amount of work that you have to do to bring a positive charge near another positive charge is the amount of work that you do. That's the amount of energy that you transfer in essence to the positive charge that you're trying to bring near the other positive charge. So let's back up a little bit. So force of repulsion. So this charge is being repelled by this charge. So when you try to bring this near the other positive charge, you have to do work on it. The closer you bring this positive charge to the other one, the more work you have to do because it's going to be, repulsion is going to get stronger and stronger as you bring this near. All right, so which means that by bringing this positive charge near this one, you end up storing energy in this positive charge. So the amount of energy stored in this positive charge is known as the electric potential energy. So what happens to that electric potential energy when you let the charge go? Notice that the electric potential energy, as soon as you let it go, electric potential energy goes down and kinetic energy goes up, which means that the electric potential energy gets converted to the kinetic energy. Electric potential energy gets converted into the kinetic energy of this charge. So potential energy, electric potential energy is the amount of energy stored in a charge, in essence. So as the electric potential energy. Case in point, once again, it's a capacitor. One region is positively charged, the other region is negatively charged. You have a positive charge here. All right, so this charge is being repelled by the electric field acting on it. So physically, you have to bring the charge near a positive charge plate. So which means that you have to do work against the repulsive electrostatic force to bring it. So which means that you end up storing energy in that object. What that means in essence is electrostatic force, just like gravity is a conservative force field. It doesn't matter that you bring it forward in this direction, okay? Or you just, path of motion is not going to matter. You can grab it and then move it around, and you can zigzag around and then do a drunken walk. In essence, you can follow a random path. it doesn't matter how you bring it near it. The fact that you're bringing this positive charge near a positive charge plate, meaning that you're storing energy in it. So the path of motion is not going to matter. All right, so by bringing it near a positive charge plate, you are storing energy in it. So it's going to have potential energy. When you let it go, what happens to that potential energy is going to be kinetic energy. And once again, the path of motion is not going to matter because the mechanical energy is constant. So it's all right, so the work done in bringing a positive charge to near a positive charge plate or a negative charge near a negative charge plate, you have to do work against the conservative force. All right, so the amount of work that you do is going to go into the potential energy.
Bob and I are
Potential energy of the charge that you're moving.
here to tell you about something that has us very
All right, so we talked about that. So capacitor is where you generate the electrons and you accelerate those electrons inside the capacitor. And remember, the guy was saying, hey, you can publish this in a high voltage magazine. Okay, so we talked about electric potential. What is voltage and what's potential? High voltage magazine, voltage and potential, they mean the same thing. All right, so positively charged region is going to have high voltage. The meaning of it will become obvious to you shortly. Just go along with it. Negatively charged region is going to have low voltage or low potential. High potential means high voltage, low potential means low voltage. All right, high voltage, low voltage. Every time there's a voltage difference, more than likely you will have lightning or spark. All right, so what's the meaning of high voltage or potential, low voltage or potential, and how does it tie in with the potential energy? Okay, one of the things that you need to understand is within this region, the electric field is going to be constant. All right, so the strength of the electric field within this region is going to be constant. Charges are uniformly distributed. All right, this place is going to be positive charge, this place is going to be negative charge. Electric field points from positive charge region towards the negative charge region. So the electric field strength is going to depend on the net charge. Okay, both places have the same net charge, this positive and negative. And the distribution of the net charge through these plates, and notice that the plate areas are the same. All right, so which means that the strength of the electric field within this region is going to be constant. If you place charge within this region, the force acting on these charges will be constant, the acceleration is going to be constant. What that means is the motion is going to be 100% predictable. All right, so inside a TV, once again, you have this capacitor. All right, so the electrons are being generated near the negatively charged region. So you got a filament, you heat it up, and the electrons are freed and they have potential energy. So that potential energy turns into kinetic energy, right? So electric field strength is constant, which means that the force acting on the charges is constant. The acceleration of each and every single charge is constant. So which means that the motion of each and every single charge is going to be predictable. So that's the reason why you can generate the images that you see on the TV screen. Everything happens because of predictable motion. Every single electron more or less is moving at the same speed when they hit this opening, the hole. All right, so because each and every single electron has potential energy. All right, so this potential energy is going to be expressed using the concept of potential. So V represents potential. All right, so what voltage or potential? So that's the concept that we will discuss right now. All right, so once again, this is known as a capacitor, positive charge region, the negative charge region. There's going to be a constant electric field within this region between the opposite charge regions that you're looking at, within the gap between two opposite charge regions. All right, guys, this is the separation distance, or the gap separation R. All right, so when you take the strength of the electric field and now multiply by the separation distance between these two opposite charge regions, you're looking at the amount of energy stored within this region. All right, so the amount of energy stored within two opposite charge regions is known as electric potential. This is the amount of energy stored within the electric field between two opposite charge regions. This is known as the electric potential or voltage that you're looking at. This is otherwise known as the voltage difference or potential difference. Okay, so what does it represent? It simply represents the amount of energy stored within the electric field between two opposite charge regions. Okay, so that's the amount of energy stored within the electric field. That's all you need to know. Now, obviously, the electric field is generated between two opposite charge regions. So that's the amount of energy stored within the electric field between two opposite charge regions. All right, so you could say this is potential difference, or you could say this is potential. So potential or potential difference, they mean the same thing. Voltage or voltage difference also means the same thing as the potential difference. All right, so when you see V, it means voltage, it means potential, it means voltage difference or potential difference. This only represents the amount of energy stored within the electric field, in the electric field between two opposite charge regions. All right, so voltage or potential, they mean the same thing. It's going to have the unit of V. V stands for volts. E represents the electric field strength. R is the separation distance between two opposite charge regions. All right, so the yellow region is where the energy is stored. Energy is stored in electric field. Electric field is where the energy is stored. What that means is, which means that the electric field has the capacity to generate a force that can cause displacement. That's it. Stronger the electric field is, more energy is stored within the region, which means that greater the capacity of this field to make charges go faster. All right, it's the same concept. So stronger the electric field is, more energy is stored in it within that region. it's just describing commonsensical ideas with tremendous amount of mathematical abstraction. That's what we're doing right now. In essence, these are the same concepts that we've been discussing. All right, so when I place a positive charge here, what happens to it? As soon as I place a positive charge, what's going to happen to the charge is it's going to experience a force in this direction, right? So it's going to accelerate in that direction. So, which means that it's going to speed up in this direction. So by placing a charge within this region, energized region, I'm able to energize the charge. So voltage and potential represents the amount of energy available in this gap, in this region. When I place the charge here, I energize the charge, which means that I take the energy from this field and transfer it to the charge. Now the charge is potential energy. Okay, so the capital U represents potential energy in this case. All right, so it's sometimes use the P, that's potential energy, or capital U, once again, it means the potential energy. Depending upon the books, it could also be V. All right, so you have these varying notations. It's the same. All right, so this V represents the amount of energy stored within this region. If you want to energize a charge, the only thing you have to do is just drop a charge into this region. As soon as you drop a charge within this region, what happens? The charge becomes energized. Now the charge is potential energy. So potential implies that the region is energized. So energy is within this region. As soon as you place the charge in that region, what happens? The energy gets transferred to the charge. Now the charge is energized. So the charge has potential energy. So what happens when you release the charge? As soon as you release the charge, this potential energy is going to turn into kinetic energy, right? All right, so what happens is as soon as you release the charge, the potential energy of the charge is going to turn into kinetic energy of the charge because mechanical energy within this region is going to be constant. Okay, so notice that we keep using the same symbols for different meanings. E represents the strength of the electric field here. E, I have to change the notation here. This is going to represent the mechanical energy. Mechanical energy is constant within this region because electrostatic force is a conservative force. So when you release the charge, what happens? Potential energy is going to go down. All right, so number one, when you place a charge, it's going to have potential energy. When you release the charge, it's going to experience a force in this direction. So, which means that it's going to accelerate in this direction, which means that it's going to speed up in that direction, which means that it's going to gain, and it's going to gain speed. It's going to gain kinetic energy in that direction. All right, so it's the same as conservation of mechanical energy regarding gravity. All right, so once again, it's related to TV tubes. All right, so here's the capacitor inside a TV tube. Okay, so this says potential energy or potential difference. In this case, it's 5,000. Okay, so I'm going to use a different one. For a TV, it's going to be old style TVs is 25,000 volts. So you're looking at the potential difference, it's going to be 25,000 volts. The electron is being accelerated in this direction, in towards the hole right there. All right, so assuming that the electron initially is not moving, so the initial speed is going to be 0. All right, so find the speed of the electron just before the electron strikes the screen. All right, just figure out the speed the moment it goes through this hole. All right, so that's what we're going to be focusing on. So it's the same formula from the formula sheet. Okay, guys, this represents the work done by a conservative force. So when the work is done by a conservative force, what happens? The potential energy goes down, the kinetic energy goes up. Negative indicates that the potential energy is going to decrease, kinetic energy is going to increase. That's what it means. And when does this happen? This happens when there's work being done by a conservative force, like gravity. Okay, when I let it go, what happens to the potential energy of this ball? It goes down, right? So what happens to this kinetic energy? It goes up. Okay, that's what the formula said. When the work is done by a conservative force, what happens is the potential energy goes down, the tide goes down, kinetic energy goes up, which means that conservative force converts kinetic energy into potential energy. That's what the formula says. So work done by a conservative force is going to diminish potential energy and it's going to increase kinetic energy. So it's going to convert potential energy into kinetic energy and vice versa. That's what a conservative force does. So C represents work done by a conservative force, so which means that kinetic energy is going to go up as potential energy goes down. All right, so when your work is done by a conservative force, what happens? Potential energy is going to go down as the kinetic energy goes up. So it's going to get converted into kinetic energy. All right, so potential energy is the potential times charge. So charge multiplied by potential means that the energy is going to get transferred to the charge. Now the charge is potential energy. All right, so the potential represents the amount of energy stored within the electric field between two opposite charge regions. So the energy is stored there. You place a charge in it, now it's got potential energy. So the potential represents the amount of energy stored within the electric field per charge in essence, if you want to get real technical about it. All right, so the volts can be expressed in terms of also joules per coulomb. All right, so you guys are not engineering students, so I'm not going to worry about it that much. Okay, so this is one of the problems that I want you to focus on when you're studying for the next test. So this is problem number 2 from the handout. All right, so that's the problem that we will focus on. All right, so the voltage or voltage difference within the capacitor inside a TV tube is going to be 25,000 volts. Electron is the one that's going to get accelerated. So here's the charge unit. Electron is a unit charge, so that's the value. Okay, and we want to know how fast it's going to be moving in terms of meters per second in terms of light speed. Okay, guys, this is Coulomb. This is going to represent light speed. This is capital C. This is lowercase c. So let's not get them confused. All right, so the electron inside the TV tube, inside the capacitor, delta V represents the voltage difference. That represents the amount of energy stored within this region. Here's the initial speed of the electron. We want to know the speed of the electron as it's going through this gap, the opening, the hole. The initial speed is going to be 0. This thing is going to speed up in this direction. Because the electric field is going to be applying a force on it in the downward direction. So it's going to accelerate in this direction. So which means that this potential energy is going to turn into the kinetic energy of this electron. So it's going to experience that force, it's going to accelerate, so it's going to speed up, so its kinetic energy is going to increase in that direction. That's what it means. So its potential energy is going to turn into kinetic energy because the electrostatic force is a conservative force field. All right, so electrostatic force is a conservative force field. So the work done by a conservative force is going to diminish the potential energy and it's going to increase the kinetic energy. So the potential energy is the potential difference times Q. This should be V, not U. Okay, cool. So it's potential difference between these two plates, or potential times the net charge is going to give you the amount of energy stored within the charge. All right, the potential difference is like the height difference. Guys, the positive or negative height difference doesn't mean anything, so which means that we will ignore that sign. When you're dealing with a potential difference, you can take this to be 0 potential and this becomes V, so this becomes potential. So potential difference is almost like the height difference, so it doesn't matter. All right, so change in potential energy can be expressed in terms of the potential difference times the charge, which means that this amount of energy gets transferred to the charge. On the right-hand side, you end up getting the change in kinetic energy. Potential difference is the same as potential, so I got rid of delta. All right, and then Q, I decided to make it E. So it's a unit charge, positive or negative, doesn't matter. Initial speed is going to be 0. So for the final speed. And then plug the numbers in. All right, so I'm trying to make the point that the negative sign doesn't matter. All right, delta V represents potential difference. So this is positive potential, this is positive potential, this is negative potential, or vice versa. You can assume one to be 0, the other one is going to be V. Okay, so it's a bit of a detail that is not that important at this point. And then you plug the numbers in, and then when you plug the numbers in, evidently you end up coming up with 95 million meters per second. All right, so let's move forward. All right, the strength of the electric field times the separation distance is going to give you the amount of energy stored within that region. So that's the voltage. Okay, so let's see a few simple problems using this one. Okay, so this is based on the previous problem. Once again, the voltage difference is 25,000 volts. Okay, so what do we know? We know the separation between the plates, opposite charged regions, is going to be 1.5 centimeters. So figure out the magnitude of the electric field. What is the strength of the electric field within this region? So that's problem number 4. All right, so problem number 2 and problem number 4 are the ones that I want you to focus on for the next task. Okay, so this is the one that we're focusing on, so problem number 4 from there on up. All right, so the voltage difference, or voltage, 25,000 volts, separation distance between the plates, it's 1.5 centimeters expressed in terms of meters. So what's the strength of the electric field? It's the same as the previous problem. This time we want to know what the strength of the electric field is. You know the separation distance, you know the voltage difference. So this would allow you to figure out the strength of the electric field. Solve for E. All right, so, okay, evidently I decided to change the problem a little bit. Okay, so solving it for E, obviously this is, okay, I'm just trying to figure out what I'm trying to do. Okay, so you solve for E and then you end up getting this number. Okay, so this is going to be almost 2 million newtons per coulomb. Okay, so by using this number, which is 1.67 million newtons per coulomb, okay, because problem number 2 and problem number 4 are related. Okay, I'm going to redo problem number 2. Instead of using the conservation of energy, I'm going to use kinematics equations. Okay, so that's what I'm going to do. Problem number 2 is kind of interesting. Now that we know the strength of the electric field, here's your unit charge. That's the electron. Initially, it's not moving. How fast will it be moving within the separation distance of 15 centimeters? Okay, I'm just changing problem number 2, so I'm just going to redo problem number 2. Instead of using the conservation of mechanical energy, this time we will get to use the kinematics equations, just for the hell of it. So that you guys understand that these concepts are related to each other. So electric field acting on the charge is going to induce a force on it, right? So what's going to happen is the charge is going to accelerate in the downward direction. Strength of the electric field is constant, force is constant. So you got a separation distance. So which you're dealing with uniformly accelerated motion, which means that you're dealing with predictable motion within that space. All right, so I decided to make R X. So I decided that this is X direction. The reason why I decided to do that, so we could use these kinematics equations. Now, kinematics equations can be used only if the acceleration is constant. So that's going to make motion predictable. All right, so assumption is that the force is constant, acceleration is constant, motion is predictable. Figure out the speed of the electrons when they're going through this hole. All right, so what do we know? We know the initial speed. We know the final speed. We know the distance x. Okay, so all right, we don't know the final speed. Get a symbol for the final speed. Anyway, so what I'm trying to say is, looking at the symbols, this equation is the only one you can use. So figure out the acceleration. You can figure out the acceleration because you know the strength of the electric field. Electric field strength is going to be constant. We discussed that before because it's a capacitor. All right, so initial speed is 0. All right, so we know the distance. We don't know the acceleration, but we know what causes acceleration is the force. Force acting on a mass is going to cause it to accelerate. All right, so electric field acting on the charge is going to induce a force on it. So do a back substitution. And the force acting on the mass is going to cause it to accelerate. So solve for A. When you solve for A, so here's what you have. Electric field acting on a charge is going to induce a force on it. Force divided by mass is the acceleration. So do a back substitution right there. Boom, boom, boom. And the mass of the electron is this. Okay, this is moving fairly fast. This is more of a demonstration thing. So you guys realize that the concepts are related. When you plug the numbers in, you end up getting the same exact numbers. So conservation of energy, mechanical energy is going to work. And conservation of mechanical energy is much faster than using kinematics equations because the concept is much more powerful. Or you could just reason through. Force causes acceleration. Force is caused by the electric field acting on the charge. The electric field is constant. Force is constant. Acceleration is constant. And then you can use kinematics equations and then figure out whatever it is that you need to figure out. Okay, so let's do a fast review. So gravitational potential energy is the amount of energy stored in an object by virtue of its position or location. All right, so you store energy in an object by actually displacing it against gravity. So it's weight times displacement, mass times gravitational acceleration times displacement. It's going to give you the amount of energy that this object has stored in it. All right, so that's in essence the amount of work done against gravity. What's gravitational potential? Something that we'll get back to shortly. What's electric potential? Electric potential is the amount of energy stored within the electric field between two opposite charge regions. Okay, so that represents the amount of energy stored within this region. Energy is going to be stored within the electric field. So that's the amount of energy stored in the electric field. So when the energy is stored within the electric field, that's electric potential or voltage. When the energy is stored within the charge, okay, it becomes potential energy. All right, so V represents the amount of energy stored within the region, and then by placing a charge within this region, you transfer the energy to the charge. Now the charge is energized, and that's got potential energy. So what's the difference between potential and potential energy? Difference is where the energy is stored. If it's potential, the energy is stored within the region. If it's potential energy, the energy is stored within the charge. That's what it means. So how's the potential related to the strength of the electric field? All right, so it is related to the strength of the electric field directly, right? So here's the electric field. So the stronger the electric field is, the stronger the voltage is. Right? So larger the strength of the electric field is, more energy is stored within that region. So the strength of the electric field goes up, the voltage goes up. How's potential related to the separation distance between two opposite charge regions? All right, the larger the separation for a given strength of the electric field, more energy is going to be stored in it. So larger the voltage difference is, the more energy is stored within that region. Because there's a larger distance that the force is going to be acting on the charge.
You're good right now?
Is it working better?
It's perfect right now.
Okay, cool, thank you. Your stuff. Okay, I hear the recording just fine now. Okay. All right, I'm good. Let's finish this up. Okay, high ground versus the low ground. All right, so why is it that it's more likely to strike high ground than the low ground? That's what we're talking about. Okay, number one, her hair is rising up because top of your body is getting positive charge. So the light charge will repel, right? So we're done with that one. All right, so this is a discussion that we had before. We will have the discussion one more time. The reason why I'm emphasizing this because this is going to be a test question, conceptual test question, more like it. Okay, so question is, why is it that high ground is more likely to be struck by low ground? All right, so quick repetition of the concepts. Clouds will become ionized first through friction among ice particles. Top of the clouds will become positive charge, and the bottom will become negatively charged for reasons we don't understand. All right, so that's the mystery. Ground is negatively charged initially. slightly negative charge, it becomes polarized and becomes positive charge. All right, so that's this quick summary. Negative charges start to move towards the ground. So these are known as the step leaders. Positive charges are going up from the ground. These are ions. Okay, so don't confuse these positive charges with the polarized surface. Polarized surface is still neutral, except, I mean, these atoms are still neutral. The atoms coming out of the, or molecules coming out of the surface of the Earth are ionized. We don't understand where we are getting these charges from. Okay, that's another mystery. Anyway, so step leaders are coming down, and then you got the streamers going up. So the streamers are positive ions going up. So when they meet in high concentrations, lightning is born. So it's an electrical discharge. The electrons get captured, and then boom. So you got the heat, you got the light, and then what else? You got the sonic boom, the lightning. All right. Separation distance for the high ground, and the separation distance for the low ground. So the lightning happens when the strength of the electric field reaches 10,000 newtons per coulomb. All right, this is a much more realistic answer. This is what it's measured to be during a lightning storm. Okay, I normally would get these numbers from Wikipedia, but this, I don't know where I got this from, because I checked it on Wikipedia about a year ago. It wasn't there, so it's certainly not 3 million newtons per coulomb. That's just ridiculously high. All right, so I made the distance to the clouds a football field in length. All right, so high ground is going to be a football field in length. The low ground is going to be 10 times the football field in length. All right, so what we are looking at is the potential difference between the high ground and the clouds and the low ground and the clouds. All right, so potential difference between the high ground and the clouds, this is supposed to be 100. Just go back and make a correction. This is going to be a million volts, and the low ground and the clouds is going to be 10 million volts. Okay, so the conclusion is it's more likely that it's going to strike high ground. Okay, so it's not the conclusion which is important. What's important is how we arrive at that conclusion. So I end up arriving at that conclusion by looking at understanding the concept of voltage and understanding the unit of volts. Okay, guys, the voltage is the amount of energy required or stored per charge to jump that gap. Okay, so the voltage potential difference is a million volts, which means that each and every single unit of charge or coulomb of charge is going to require about 1 million joules of energy to jump that gap. Okay, so which means that the amount of energy required to jump that gap in this case is going to be 1 million joules of energy per coulomb of charge. That's what it represents. All right, so in order to jump a distance which is 10 times larger, you need 10 times the energy, right? So which means that the charges will require enough energy to jump a shorter distance before they require enough energy to jump a longer distance. Okay, so that's straightforward. So if this logic is correct, 100% of the time it should hit high ground. All right, so 100% of the time it should hit high ground. Except life is not this easy. What's happening in real life is 70% of the time this logic works. 70% of the time the high ground is going to get hit. Instead of 100% of the time, this is 70% of the time. Okay, 70% of the time this is what you get. 30% of the time the low ground gets hit. Okay, these are rough estimates and not exact numbers. So the question is, why is it that 100% of the time the high ground is not getting hit? Because the charges should require enough energy to jump this gap, so the discharge should happen when the distance is shorter than when the distance is longer, because they will have to require a lot more energy to jump this gap, and they would have enough energy to jump this gap actually sooner. By the time they require enough energy to jump this gap, they already have enough energy to discharge through jumping this gap. All right, there's a bunch of reasons for it. Number one, the charges are not uniformly distributed. It's not like a parallel plate capacitor. So the strength of the electric field is not going to be uniform. All right, it may be 10,000 newtons here, it may be much less than here. So what that means is the charge distribution here is not going to be strong enough. So you don't have a strong enough charge distribution here. You may have a strong enough charge distribution here. So most negative charges are going to be here, or most positive charges will be here. Or you may have a lot of negative charges here. You may have a lot of positive charges here, and the positive charge distribution may be weaker here and there. So all of a sudden, the shortest distance between two opposite charge regions become this distance or that distance. Okay, so because the charge distribution is not uniform, all right, you cannot tell with certainty that this is 100% certain that it's going to strike high ground. So there's randomness involved when it comes to lightning. All right, case in point, obviously. All right, so this used to be my school in Chicago, and the distance between this school and Sears Tower and Willis Tower, right, they're a mile apart. That's it. Okay, so this is high ground. This thing is 1,500 feet tall, all the way to the top of the antenna, and this building is not as tall, obviously. And so why is it that this building is getting hit and not that building? Okay, the reason is because obviously you have a stronger positive charge density here, and then you have a stronger negative charge density here. So this distance from clouds to the ground tends to be shorter than this distance between the Sears Tower and the stronger negative charge distribution here. So you've got this distance is going to be less than a mile. This distance is going to be more than a mile. Despite the fact that it's a taller building, you have a much stronger oppositely charged regions within this gap that you're looking at. So that's the explanation. Okay, so speaking about mathematically, the conceptually this stuff's kind of taxing, but mathematically it's not bad. Okay, so let's talk about voltage or potential.
Can I ask you a question really quick?
Yeah, go ahead.
All right, yeah. So in terms of that picture that you showed us, I know you said that it's based on having a higher positive charge in that area relative to the, I guess, the Willis Tower. Does the cloud position factor into that at all as far as polarization?
It does, absolutely, yeah. I mean, which means that cloud position and the position of the charges, the distribution of the charges within the cloud. All right, under the clouds, the charges are not uniformly distributed either. Okay, so you happen to have a very strong negative charge concentration here. The cloud may be extending maybe about a mile in this direction, but the negative charge distribution, the concentration density, okay, that's the term I want to use. All right, density of the negative charges above the Willis Tower is probably not as strong, but here it's much stronger. And another thing is, for whatever reason, these positive ions, for whatever reason, have a much strong density around this building somehow. All right, so and as a result, then the charge concentration of the positive charge is not as strong here for whatever reason. So you can't tell where the charges are because you can't see them. But nature usually takes the path of least, the shortest path. I'm just going to say the path of least resistance. I don't like that term that much. There's a good reason for it, but it's going to take the shortest distance between two opposite charge regions. The shortest distance between two opposite charge regions is low ground getting hit, because this is a strongly positively charged region. This is a strongly negatively charged region. And only this region is strongly negatively charged, not the region above the Willis Tower. Okay, so give yourself 10 points. Yeah, I think you got a good. Okay, so I'm gonna give you an analogy because I think this analogy is gonna work the best. It's not just this high voltage, low voltage, blah, 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 representing the amount of energy stored within the strength of the electric field. That's just too much to remember. It's just too abstract. Okay, I love the gravitational analogy. Okay, so potential energy is the amount of energy stored in the masses, right? So how do you store energy in these masses? By lifting them up against gravity, just lifting them up. So you do work against gravity. Now they got energy stored in them, right? I just lift the ball, I energize the ball, it's got potential energy. Okay. So both of them are at the same height. Do they have the same amount of potential energy? Well, no, because they don't weigh the same, right? Okay, they don't have the same mass. Okay, they don't have the same potential energy. Okay, so potential energy is the amount of energy stored in an object by virtue of its position, as well as its weight, obviously. So weight matters because it represents the amount of work you have to do in order to lift this thing up against gravity, which means that heavier the object is, the more work you have to do in order to lift it up. But now let's move on to the concept of potential. Potential is the amount of energy that the gravity has by virtue of its position. All right, so potential only represents height, guys. That's it. All right. So if there's any sort of potential difference, that implies height difference. So notice that the masses go from a higher potential towards the lower potential. So if there is a potential difference, the objects will move or fall from a higher potential towards the lower potential. What that means is they will fall from a higher altitude towards the lower altitude. Yeah. So when gravity does work, and then conservative force acts on something, it's going to move things from a higher potential towards the lower potential. So potential represents height. Every time you get confused, if somebody's talking about potential difference, if there's a conservative force involved, things will go from a higher altitude towards the lower altitude. All right, the same thing is true regarding charges, guys. If there's voltage or potential difference, it's like that height difference. Okay, positive is going to be at a higher altitude, the negative is going to be a lower altitude. It's the same idea. Think of it in terms of altitude. All right, so gravitational analogy, when and if you're confused, is something to fall back to. All right, and then always think of positive charges. What would a positive charge do? Okay, so positive charges will always flow or go from a higher potential towards the low potential. So when there's a potential difference, we're talking about a height difference, the masses will fall or move from higher altitude towards the lower altitude, or they will flow, if it's like water, from a higher altitude towards the lower altitude, and the charges will move or flow from a higher voltage towards the lower voltage. So if there's voltage difference, charges will always move when left alone. They will always go from a higher voltage towards the lower voltage. Okay, when we're talking about charges, unless stated otherwise, think of positive charges. Okay, so if you're thinking negative charges, it's going to cause a confusion. And let's not go there immediately. Let's just get used to the positive charges. Positive charges under the electrostatic force is going to behave like mass under the influence of gravity. Our negative charges will move in the opposite direction, but let's stick with the positive charge notation for now. All right, so the altitude is going to represent voltage or potential. Points at the same altitude are said to be on the same equal potential. Okay, so the term equal potential means points at the same altitude is going to have the same, they're going to have the same voltage, they're going to have the same potential. All right, so which means that each and every single point, if they're at the same altitude, at the same height, they will share the same height, voltage, the potential. That's what it means. So this gravitational analogy of height is going to serve us really, really well in terms of the understanding of the concept of voltage. All right, so 25 meters is going to represent the voltage at this altitude. So every single point in this circle is going to be at the same height, which means that this is an equal potential line. And if you think of it in terms of two-dimensional area, every single point is going to be at the same voltage or potential. All right, 20 meters, likewise, is a different equal potential surface. 15 meters is an equal potential surface. All right, so it's the same idea, guys. The positive charge right here. All right, so this is an equal potential surface. Every single point is going to be at the same voltage. That's what it means. So which means that the strength of the electric field, the amount of energy stored within the electric field at these points will be the same, right? So the further away you get from the positive charge, the weaker the strength of the energy is going to become. All right, so the amount of energy stored within this region, okay, within this line, within this curve, is going to be strongest near the positive charge. The amount of energy stored within the field, as you start to move away from the field, is going to get weaker and weaker and weaker. All right, so which means that further away you get from the field, the amount of energy stored in the field is going to get weaker. So that's the simple way of looking at it. So at the same time, on the equal potential surface, okay, so at this line, all right, each and every single point is going to have the same amount of energy stored in them. That's what it means. So here's your equal potential surface. Here's your equal potential surface, whatever. All right, so the charges can move on these equal potential surfaces without gaining or losing energy. All right, so the potential energy of the charge is going to remain the same, even if it's moved from this point to that point. So none of that energy is going to get transferred to kinetic energy. So the path of motion doesn't matter. Notice that the charge can move from this equal potential surface to the other one. When it does, okay, its potential energy is going to change. And it doesn't matter that you move the charge this way or that way. All right, the path of motion does not matter. If the potential energy goes down, if the potential goes down, if the potential energy goes down, the kinetic energy is going to go up. Okay, so that's what it means. It's despite the fact that the charge is doing this, there's no change in potential. So which means that no change in potential energy, there's no change in kinetic energy. Once again, guys, abstraction after abstraction. But you will catch up shortly. All right, so the point charge, let's talk about the point charge. So what's happening is if you bring this positive charge near this one, you're gonna energize it. All right, so which means that you will be able to store potential energy in this charge. Okay, just bringing it near this one, which means that you have to do work against the electrostatic repulsion in order to bring it nearer. Okay, the thing of it is the positive charge is going to act like a hill. All right, it's like bringing this positive charge near another positive charge. It's almost like climbing up a hill. So closer you get to it, the larger the potential is going to be. Positive charges will represent high potential. The negative charges will represent low potential. Positive charges will represent positive potential. The negative charges will represent negative potential. Positive charges will represent higher voltage. The negative charges will represent lower voltage. Let's talk about that. All right, so this is the potential of a point charge. So there's something about it that I set it up just nicely, except don't want to go to a formula right now. All right, guys, just bear with me. I have to change the order of the presentation. Okay, so just using a formula at this point does not help with the problem. Okay, so it's better to just keep things visual just for now. I'm trying to build up your intuition. All right, this is good. All right, now that I mentioned it, let's get back. Okay, so positive charge near a positive charge. All right, so I'm forcing this positive charge. I'm moving the charge towards the other positive charge. And it's almost like climbing up a hill, okay? Because closer you get to this positive charge, the harder it's going to be to bring it nearer, in essence. All right, so the more work you have to do in order to bring it nearer and nearer, closer to the positive charge, which means that the hill is going to become steeper and steeper and steeper. So the closer you bring it to it, the higher the energy that you're storing in it, in essence, so higher the potential energy is going to become. From a gravitational analogy, it's like the steeper the hill becomes, higher up you go, the more energy you store in the object that you're lifting or climbing. Yeah. So this analogy is going to look like this. Okay, the positive charges will look like hills. Okay, so if you think of voltage or potential in terms of altitude, all right, so near the positive charge, the field is going to, the voltage field, the potential field of potential is going to look like a hill, almost like a spike. Okay, so you bring a positive charge nearer. Okay, so what happens is it's like climbing up a hill, so more energy you end up storing in it, so the potential energy of that charge is going to go up. So positive charge represents positive voltage, positive potential, it represents a hill, guys. This is a three-dimensional mechanical analogy of a hill works for something. Negative charge represents a well. This is known as a gravitational well. So positive charges will give you a hill, the negative charges will give you a well. Potential difference is the height difference. Right? Look at the peak of this hill and look at the bottom of this well. All right, so the positive charges will represent high potential, higher altitude. the negative charges will represent low potential, lower altitude. Okay, this is a zero potential surface. Okay, so this is zero potential, positive potential, zero potential, negative potential. Okay, so if you're talking about positive and negative, you have to talk about positive and negative with respect to a reference surface. So here's your reference surface. So this surface is going to be exactly zero, usually at infinity. At infinity, you will have zero potential. So if closer you get to the charge, the larger the potential becomes near a positive charge. Closer you get to, okay, so closer you bring a positive charge near a negative charge, it's almost like, for a positive charge, it's almost like falling into a hell. So it's just going to keep speeding up in this direction. That's what it means. All right, so with reference to a positive charge, negative charge is going to become very attractive. In reference to a positive charge, the positive charge becomes extremely repulsive. It's like climbing up a hill. Relative to a positive charge, the negative charge is going to become very attractive. It's almost like flowing or running into a hill, running into a well, more like it. All right, so these are visual constructs.
By the same token, the contours on this map give a clear representation of an electric field. These are contours of constant electric potential, and they too represent terrain that has ups and downs.
Sound is distorted again.
Okay, let's again. Hey. Okay, I think this is done. Okay, so we're back in business, I think. All right. Right. Let me just check something real fast. Okay, thank you for the feedback. All right, guys, just feel free to jump in. If you have any questions or whatever, don't hold back. We're not in a hurry.
When real ground goes up and down, the prudent traveler wants to know about it, because going uphill can be hard work. And exactly the same is true for electric potential.
Okay, one more thing. Sometimes, obviously, we end up getting static because my computer got like 1,000 things running in the background. I'm working on research during the day, and I do a lot of coding. And part of it, this video, the audio quality of this video is horrible. Okay, this is a video that I got from a library, which was originally made in 1985. It's known as Mechanical Energy. This is done by Caltech. And so I was digitizing it with the technology that I had 20 years ago. And at the time I was living in Buffalo Grove next to a radio station. Okay, and unbeknownst to me, when I was actually digitizing it, my the video editor was picking up the sound from the radio station. So if you hear some kind of background music, some static and background music is coming from there. Okay, so it's just be aware.
Moving up the incline of potential is hard work. And the steeper it is, the harder it is to climb. Of course, if the potential isn't changing, it takes no work at all. And if the potential decreases, the field is downhill all the way. In this analogy, electric potential is elevation, and electric field is the downward slope.
All right, so we got that analogy. All right, now let's talk about the potential due to a point charge. Already gave you that one. So this represents okay, so I'll just have to stop one more time. Okay, and okay, so finally, all right. I want to explain the meaning of the potential due to a point charge. Okay, so here's your positive charge. Positive charge is going to emit the electric field. So the electric field is being emitted or transmitted by the charge, right? The positive charge is a transmitter in this case. So electric field lines, notice that they're pointing in this direction. They're pointing in radial directions. And this is like a hill. And so these are equal potential lines. Notice that the voltage is going to decrease in the direction of the electric field. All right, so this point is going to have a higher voltage. This point is going to have a lower voltage. The next point is going to have a lower voltage, and so forth. Okay, so how do we know the voltage values due to a point charge? All right, so what is the value of the voltage at this point versus at that point? So R1 is for the first equal potential, R2 is the second equal potential. So what are these voltage values relative to the positive charge? All right, so that's what this formula gives you. All right, so here's the strength of the electric field. Ignore the details. This is for this is calculus. All right, so this voltage that you're looking at, this signifies the voltage value due to point charge at this radial distance. All right, a certain radial distance. So if this is R1, it's going to give you V1. If this is R2, it's going to give you V2. So notice that further away you get from the charge, the smaller the voltage is. And if there's a voltage difference, like the height difference, this ball, if it's a hill, for example, it's going to roll from a higher altitude towards the lower altitude. So closer you get to the tip of this hill, this higher the altitude is, obviously, the more energized the ball becomes. And when you let it go, it's going to go from a higher altitude towards the lower altitude. So this allows us to be able to actually come up with values for the voltage around a point charge. Okay, so that's the meaning of the formula. All right, so this represents the electric potential due to a point charge. So the Q represents the point charge. R represents the location, radial distance, the radial location, radial distance away from the point charge, where you're interested in the value of the potential is. All right, so further away you get from the point charge, the weaker the potential is going to become. So that's all right. So the stronger the charge is, the larger the voltage is. Larger the distance is, the weaker the voltage. All right, so pick out the best answer and just put it in the chat. All right, so, okay, you guys got it. If I double the charge, or I guess if I double the charge, it doubles the voltage, right? All right, so if I double the charge, it doubles the voltage. That's it. All right, so you guys got this. All right, you give yourselves 5 points for that one. So be the best answer for that one. Okay, another thing that I want you to notice is, I kind of made this poem, but I'm going to make it again. Notice that the electric field starts at a positive charge, ends on a negative charge, right? So take a look at the electric field lines. They start on a positive charge, they end on a negative charge. They will always point in the direction of the decreasing potential. All right, so there's a positive charge. All right, so you get an equal potential here. And then when you start to move away from the positive charge, notice what happens, the potential gets weaker and weaker and weaker. That's what it means. So the electric field lines will always point in the direction of the reducing potential or decreasing potential. Another thing that I want you to notice is electric field lines will always be perpendicular to these equal potentials. All right, so take a look at this. Electric field is going to be perpendicular to the equal potential. It's going to be 90 degrees to equal potential. It's going to be 90 degrees to equal potential. All right, so potential is something that you can measure. Okay, obviously we're not able to do labs at this point because nothing is in person. Normally we would have voltmeters around charges or charge regions. We could measure the voltage, so you could measure the equal potential lines, and then you would draw perpendicular lines to figure out the direction of the electric field, so you could actually map the entire region. All right, so this stuff which is important is here's the direction of the electric field. Electric field lines will point in the direction of the decreasing equal potentials. All right, here it's still moving in the direction of the decreasing equal potentials or decreasing voltage. All right, so the voltage is negative around the negative charge, so it's going to be low voltage here, it's going to be higher voltage here. All right, so let me check to see. All right, so I'm going to make the same statement. This says, okay, so ignore this because it's from calculus. Here's what you're interested in. All right, so here's positive charge region. Electric field is pointing away from the positive charge region. Okay, so the amount of energy stored within this region is going to diminish as you start to move away from the source. All right, so the electric field is still going to point in the direction of the diminishing voltage. All right, so that's what it means. So electric field is going to point in the direction of the decreasing voltage. So the electric field is, this is a high voltage region, this is a low voltage region. So which means that the electric field points from a positive charge source to negative charge. And that's, I'm saying the same thing. Positive charge region is going to be high voltage, negative charge region is going to be low voltage. So the electric field always points from a high voltage towards the low voltage. Okay, so just remember that. So negatively charged region represents the negative potential, positive charge region represents the positive potential. When there's a potential difference or voltage difference, the electric field points in the direction of the diminishing voltage. So the voltage is diminishing in this direction. Okay, and that's the reason why there would be a negative sign usually right there. right in front of it. And then I'm turning this into calculus for the calc-based course, but it's the same. I just wanted you to get that.
What does the electric field for this potential look like? Because it takes no work to move a charge along a curve of constant potential. There's no component of field in that direction. So the field is perpendicular to each equal potential at every point. And that's how it assumes its familiar shape.
All right, so problem number six. Okay, I want to do this problem and then go take a break. Okay, so like I said, the hydrogen atom is a big deal. The simplest atom in the universe. And then we're going to go through the evolution of the hydrogen atom all throughout physics, because we will also cover modern physics in this class. Okay, so you can see what happens to the atom. Okay, remember we talked about ionization. Okay, so what's ionization? Ionization is stripping atoms of their electrons, right? So process of stripping electrons from atoms is known as ionization. Okay, so we've seen friction will do that. Also, we also know that heat does the same thing, because we were talking about a filament inside the capacitor of the TV tube. You heat it up, it would just give up its electrons, right? Okay, so every single atom has a known ionization energy. Okay, so what's the meaning of an ionization energy? Those of you guys have taken chemistry, I think just about every single person has. They always talk about ionization energy of this and that, so that's important in terms of chemical reactions. All right, so what's the meaning of ionization energy of an atom? Ionization energy of an atom is the amount of energy required to free an electron from an atom, guys. That's it. All right, so the ionization energy of an atom is the amount of energy required to knock an electron from an atom. Okay, so the question is, hydrogen atom, every single hydrogen atom is going to have exactly the same ionization energy. If you provide an atom the exact energy required, exact energy requirement to free an electron, it's just you give the atom the energy and then it's just going to give you the electron. That's it. It's like a money exchange. Okay, so there's a price tag involved. That's known as the ionization energy. In the case of the hydrogen, it's got to be a 13.58 eV, or known as electron volt. Every single hydrogen atom can be ionized at 13.58 eV, or electron volt. All right, so the question is, how do we compute this? How do we know what the value of it is? Okay, so this is simply not a problem. So I'm just gonna do that problem. It's simply not, but let's do it anyway. It's gonna take. So in essence, it says it's the electric potential, it's the total energy, the ionization energy of the atom. Instead of breaking it into three parts, I'm just going to attack this problem. So the ionization energy of the hydrogen atom. So we know the size of the atom. Okay, so we'll express it in terms of 10 to minus 10 meters. 10 to minus 10 meters is an angstrom, so it's, the distance is in half an angstrom. All right, so what's the ionization energy of the hydrogen atom? Okay, it's going to look like it's a math problem. It's not. The problem is done using math, but it's not a math problem. All right, so the ionization energy is 13.58 EV. All right, so it's going to say 13.6 EV approximation. There's going to be a negative here, so we have to discuss the meaning of negative. All right, so we got the hydrogen atom. All right, so here's the radius. I'm expressing it in terms of 10 to minus 10. So that's half an angstrom. All right, so this means the ionization energy in terms of joules. All right, and then we will have to express it in terms of EV, electron volts. Okay, electron volt is something that we use in modern physics. All right, so we're dealing with atoms, so this is known as atomic physics. In chemistry, also, it's used in chemistry as well. In classical physics, we use joules. All right, so the charge, net charge inside the atom, positive or negative. Negative is the electron, and positive is the proton. All right, so both of them are unit charges, positive or negative. You will also need the mass of the electron. Okay, now let's discuss the meaning of the ionization energy. So what's the meaning of the ionization energy? Okay, so what do we compute it when we're dealing with the ionization energy? All right, so here's what you're looking at in terms of the atom. Simplistic model of the atom that we're using. Ionization energy is the amount of energy that you have to give this atom so you can just knock this electron out of this atom. All right, so that's the amount of energy that you have to provide the atom. So atom goes, okay, so that's the fair exchange. I'm just going to give you my electron. All right, so that's the ionization energy. Okay, so the question is, now that we know what ionization energy is, how do you compute it? What is it that you have to do in order to compute it? Okay, so one thing that you need to know is you've got the positive and negative charges, and positive charge is the emitter of the electrostatic force, and you know it's a conservative force field, and this force extends all the way out to the negative charge. So it's going to transfer energy to the negative charge. So which means that this, okay, so positive charge, okay, so I got to say this, I will try to say this just right, okay, but I'm not going to try to get it perfect. Okay, so I'm gonna keep saying it, changing it slightly. I'm gonna keep varying this statement. Okay, so this is an electrostatic force field. This is a conservative force field. Whatever this region is, within this region, the mechanical energy is gonna be conserved. All right, so we got a positive and negative charge. There's a separation distance between positive and negative charges. Okay, so which means that energy is already stored within this region. The amount of energy stored within the region between regions of two opposite charges is known as potential, right? All right, so, and this is a point charge, and so this is an equal potential surface or equal potential line. So which means that there's voltage here, and when you place a negative charge within this equal potential, this negative charge is gonna have potential energy. All right, now it's gonna have potential energy. Also, it's moving, which means that it's also got kinetic energy. So which means that the charge already has a mechanical energy. So this represents the mechanical energy of a charge. Okay, I made it a fancy E. I just made it wiggly E, whatever that is. I'm just making things up right now. The reason why I decided to make this look wiggly or fancy because I don't want this to be confused by this one. Okay, this is the electric field. This is the mechanical energy. All right. Notice that when you come up with a model and when you're trying to figure out the mathematics, everything comes out of your conceptual understanding of what's going on. Okay. I mean, you could just, of course, cheat. You can copy formulas from a formula sheet or just from books, but that's, you don't really learn anything doing it that way. The whole idea is imagine that you're the first person. First person in history who's trying to solve this problem. How would you look at it? And I would look at it from the way I'm looking at it. Literally, it's something I already have the concepts. Just keep applying the concepts. All right, so you got two opposite charges. So there's a separation distance. So there's voltage here, and the voltage is going to be the same at equal distances. So this is an equal potential. So which means that voltage within this perimeter, otherwise known as the orbital, is going to be the same. If there's a charge on it, okay, by virtue of being there, now it's got potential energy, and because it's moving, it's also got kinetic energy. So a combination is going to be mechanical energy. I know the mechanical energy is going to be constant within this region because the electric field is a conservative force field. That's it. That's everything that we discussed. All right, that's it. Okay, so this is the mechanical energy of this charge. Okay, so if I want to free this charge from this atom, this charge is going to require this much energy. So this becomes the ionization energy of this charge in essence. All right, so this is the amount of energy that this charge already has. So if I want to free this from this atom, I have to say, okay, so here's what you need. This is the price of freedom at this point. So this is the amount of energy that it's going to require in order to free itself from this atom, because it's a captive of this atom at this point. All right, so that becomes the ionization energy. And this is like storytelling at this point. All right, so the question is, how do we compute that ionization energy? It's straightforward. Kinetic energy is going to be 1/2 mv squared. And the potential energy of the charge, you know, we got the potential because there was an equal potential due to the proton. And then I place my electron right there. Electron is a negative charge. And all of a sudden, this voltage or potential due to the positive charge, proton. And when you place an electron there, now the electron is going to have potential energy. And so this represents potential energy of the electron. Potential energy of the electron is going to be negative, but whatever that means, we'll find out. All right, now this is voltage or potential due to the positive charge. The positive charge acts like a point charge. All right, so the voltage at this radial distance is going to be given by this formula, so we will do a back substitution. All right, so our formula is going to look like, all right, so this is KER, and we have one more E there, so this is going to be E squared divided by R. Okay, now we've got, these are unit charges squared. K is the strength of the electrostatic force. R is the separation distance between the proton and the electron, obviously. Okay, so this is the mass of an electron, this is the speed of an electron. All right, so we know the mass of an electron, we know the unit charges. We also know R, but we don't know the speed of an electron, except we kind of did learn how to compute the speed the first week, or the first chapter. All right, so how do you find the speed? You know, this is circular motion. All right, which means that we have to utilize the concept of centripetal force, right? Center seeking force. Centripetal force, once again, is the electrostatic force. We've done this round before. Generic expression for the centripetal force is mv squared divided by R. Electrostatic force is the Coulomb's law. So the centripetal force is the electrostatic force, so which means that you can equate the right-hand side. And solve for V, so R squared, so one will cancel on the right-hand side. Okay, and get rid of, oh, okay, so now I'm doing something cute. Huh. All right, I'm doing something cute. Move back. Okay, take a look at the expression for kinetic energy. It's going to be 1/2 mv squared. This is mv squared, all right, equals Ke squared divided by R. Mv squared here equals to the potential energy of the atom in essence. Okay, but if I divide this by half, by 2, this becomes kinetic energy. So which means that if I divide the left-hand side by 2, I have to divide the right-hand side by 2. Okay, so I'm using a mathematical trick that we employ It's because I'm looking for an expression for the kinetic energy. Now I came up with an expression for the kinetic energy, and this expression for the kinetic energy is the same as half the potential energy of the atom in essence. All right, so I can just plug it into that formula. All right, and so notice that this is half the potential energy of the atom, and this is the full potential energy of the atom. And then if they have a common denominator, so you can multiply and divide by this by 2, now they have a common denominator. And then when you plug the numbers in, it's going to give you an expression in terms of voltage, but that's not what I'm interested in. Okay. And then what I'm going to do is, this is E squared, so I'm just going to split E's. All right, so I'm going to take this E out. This is KE divided by R. This is a voltage term. So I'm just going to keep E out. I'm going to compute this one. Okay, so it's going to be E divided by 2. I'm going to leave E here, 2 there. And when I compute that, it's going to give me 13.58 volts. All right, so it's going to give me the voltage term in terms of volts. It's going to be 13.58. And then if you use E as a unit and place it in, it's going to give you 13.58 EV. So this becomes the ionization energy. All right, this was a lot of blah, blah, blah. I don't know how well you were able to follow this. It's not that important because I'm not going to ask you to replicate this, but I just wanted you to see where we get these concepts from. Okay, so this computation of the ionization energy comes from the conservation of mechanical energy, and this is a somewhat sophisticated application of the concepts that we discussed so far. The only thing that you need to know out of this is obviously the meaning of EV, that's the electron volt. Joules is what we use, and the ionization energy represents the amount of energy required to strip an electron from an atom. All right, so the ionization energy of an atom is the same as the mechanical energy of an electron in this case. And so you could see somewhat of a sophisticated application of this concept. Another thing that I'm going to ask you is this one, this negative value. All right, so what is this represent? What's the meaning of this having a negative value? Okay, expressed in terms of EV. Guys, the negative value represents when you have an ionization energy which is negative. And if you're looking at it, the reason why this becomes negative, when you look at the mechanical energy of this one, here's the kinetic energy term, is the potential energy term. Okay. The only way you will end up getting a negative energy out of this one is if the potential energy is negative. All right, if the potential energy is negative, which means that potential energy is going to be larger than the kinetic energy in this case, and negative potential energy is going to act like a potential well. It's almost like the electron is inside a potential well, which means that it's stuck inside a potential well. So the negative value represents an attractive force. It represents a potential well, which means that if the ionization energy is negative, which means that this electron is a captive inside this potential well. That's what it means. All right, so it's going to act like a potential well. Okay, I'm just trying to get up. All right, so that's portion is going to act like a potential well right there. All right, so here's your potential well. If the electron is outside the potential well, it's going to have larger kinetic energy than the potential energy. All right, so the potential energy, imagine that this is going to be 0 here, it's going to be negative here. So negative potential energy means the electron is a negative potential energy, which is larger than its kinetic energy, which means that it doesn't have enough kinetic energy to get itself free from this well. Right, so that's the visual form, which means that it's trapped within the well of the atom. Okay, because this is the terminology we use in modern physics all the time. You may have heard the gravitational well, blah, blah, blah. It means the same thing. All right, so it's once again, it's 0 potential represents a flat surface. It doesn't have any height. All right, so if you're above the surface, it's going to represent positive voltage. If it's below that, it's going to represent negative voltage. Okay, so in the case of the electron, it's almost like trapped within the well because it's got negative energy, it's got negative potential energy, which means that it doesn't have enough kinetic energy to leave on its own, on its accord. Okay, this was just too much talking. All right. Okay, guys, it's 8:52. We got a few things to cover and then we're done. So I'm going to give you like 10 minutes. And then we'll finish it up. The rest of it is just conceptual. All right, take a break until 5. Okay, isolated conductors.
Lightning. It is one of nature's most awesome forces, yet much remains to the atmosphere. Spider lightning, difficult to tame the unpredictable. Why this mysterious form of lightning travels along the base of the storm, sometimes for hundreds of miles instead of striking down to the ground, is not understood. For decades, scientists struggled to tame the unpredictable and destructive forces of lightning in order to study it in a controllable manner. The result was an entirely new kind of discharge, triggered lightning. Langmuir Labs, high above Socorro, New Mexico, is a lightning lab in the clouds, a place uniquely suited for triggering lightning. Here, Professor Charles Moore has been studying lightning phenomena for almost 40 years. We have students here that have gotten to be quite proficient in triggering lightning, initiating lightning by firing these small rockets that we have here up into the air beneath the cloud, pulling a wire, a grounded wire, and this intensifies the electric field at the tip of the wire so much that lightning actually initiates off the tip of the wire and races on up into the cloud. It's just, we call it triggered lightning, but really it's initiated lightning.
The lightning is triggered when a toy rocket pulls the positive ground charge up into a cloud at just the right moment, seconds before the cloud is ready to unleash a lightning bolt.
The rockets that we use are very small and inexpensive, and they're essentially expended whenever they're flown. The wire that that's pulled up first gets melted, and then it gets vaporized, and so there's a very strong bar of light. It looks for all the world like the bar of light from Star Wars.
By triggering strikes above sophisticated sensing devices, Moore and his colleagues hope to increase our knowledge about lightning currents, temperatures, and discharge patterns.
Lightning itself is a very dangerous phenomenon. Their energy equivalent to about 2 tons of TNT released in a discharge. But here on the mountaintop, we have an underground steel room. We call it the Iron Kiva, in which we constructed to study lightning. And inside it, we're quite safe when we have lightning strike. On the mountain, which we can.
Notice that when they're studying lightning, they're inside a metallic enclosure, right? Okay, so that's going to be one of your test questions. If you're trying to protect yourself from lightning, what do you have to do? Make sure that you're inside a metallic enclosure. You have to be inside a metallic enclosure in order to protect yourself, because the net charge is going to remain outside.
To study lightning, and inside it.
All right, so the same thing goes for the person inside the car. All right, so the electricity is going to remain outside. As long as she remains on the inside, she's going to be fine. So this is something that we ended up discussing before. But the question is, I said, even if she's touching the outside of the metal, she's still going to be fine. So the question is, how's that possible? All right, so you know that the excess charge is going to remain outside of the metallic enclosure. All right, so the net charge on the inside is going to be 0. And then now let's take a look at the potential difference between inside and outside this region. Okay, so this is your hollow conductor. So this is like a car, the airplane, or it could be, it's like a Faraday's cage, it doesn't matter. Okay, so notice that if there's potential difference, the electric field is going to point from higher potential towards the lower potential. So what is the potential difference between inside and the surface of a hollow conductor? So what is the potential difference between the inside and the surface of a hollow conductor? Guys, there's no net charge on the inside. Inside, the electric field is going to be 0. 0 times the separation distance between the center and the outside is going to be 0, which means that the voltage and potential difference between inside and outside of a hollow conductor is going to be 0. If there's no voltage difference between inside and outside, if there's no electric field between the inside and the outside of a conductor, there's no voltage difference. So the voltage inside and the voltage at the surface will be the same. If there's no voltage difference, there's no electric field pointing in or out of this conductor, which means that there's no potential difference between the surface and the inside of the surface. If there's no potential difference between the surface of a conductor and inside of within the conductor. Okay, so the entire setup is an equal potential, which means that there's no reason for charges to go through your body, even if you're touching the outside of the vehicle. Okay, because inside and outside of the vehicle is at the same voltage and potential. In essence, that's the reason why you're going to be 100% safe. Let me just give you the same expression. All right, so here's the vehicle. You're inside the vehicle, and the vehicle is extending this way. This says 1 meter, okay? All right, and you're inside the vehicle. You're sitting here, and then you're extending your hand out. And so this is the outside of the vehicle, so you can touch the outside of the vehicle. So there's no potential difference between inside and outside of the vehicle, so you're not going to get shocked. As you start to move away from the vehicle, the potential is going to get reduced. So there's going to be a potential difference as you start to walk away. So you're here, if you step outside, there's going to be a potential difference. But if you're touching the outside surface, inside and outside, there's no. Inside, the electric field is going to be 0. The outside of the right, like when you touch the metal of the field, the electric field is going to be 0. So there's no electric field between inside and outside of the field, inside of the car, in essence. So you can touch the metal, it's still going to be fine, as long as you remain on the inside. As long as you're not touching the ground. You're not touching the ground outside of the vehicle. All right, so I'm just curious if you guys will get this one right. So we got a hollow metallic sphere. So it's charged to the potential V, which means that the outside is charged. So which means that it's got net charge outside. So what's the potential at its center? Okay, so yeah, okay. I'm gonna give you guys 5 points for picking the wrong one. All right, guys. If the outside potential is V, the inside potential is also going to be V, right? So there's no potential difference between inside and outside. Okay, that's the meaning of it. All right, so there's no potential difference between inside and outside. All right, so potential difference usually happens in the direction of the electric field, obviously. There's no net charge on the inside, there's no electric field on the inside. So there's no potential difference between inside and outside of the vehicle. All right, so the best answer is okay, so you guys got it wrong about this particular learning answer. All right, so that's important.
Hello?
All right, so let's visualize the concept for you guys in a real life.
Sorry, my meeting ran late. I should be home in about a half an hour. Sure, I can pick up dinner. What do you want? Hot and spicy. That's what I'm talking about. I will. I love you too.
Whoa. Oh, man. So that's what an airbag feels like. My car. Great. I should probably get out and see how bad the damage is. Wait. Are those telephone wires or power lines? Yeah, either way, they could be hot. No way to be sure. Don't take any chances. Just stay in the car and call 911. Good thing I actually paid attention during that safety meeting. Hi, this is Stephen Stonebanks. I've been in a car accident. I hit a power pole. I'm on Highway 18, somewhere east of the 356th Street exit, a couple of miles. No, I'm okay, but there are power lines on my car. Okay, yeah, I know. I won't move until you tell me that the line is de-energized. Yes, I will stay put. Okay, please hurry. Thank you. Honey? Listen, I've been in an accident. I'm fine. I hit a power pole. The car is a mess, but I'm okay. Yeah, I've called 911. They're on their way. Oh, no. Hey!
Are you okay?
Hey, stay back! No, don't come any closer. You could get shocked by the ground around these down power lines. Stay back about 35 feet and make sure no one else comes near.
Okay.
I called 911. They're on their way. Thank you. Honey? No, I'm fine. No, don't worry. Yeah, the police are on their way. Yeah, all I've got to do now is sit and wait. Honey? I gotta call you back in a couple of minutes. Oh boy, not good.
Oh my gosh.
Okay. Plan B. Exit the vehicle. But now I gotta worry about touch potential.
Okay, so that you cannot do. Why not?
Touch potential is risk of electrocution based on one part of the body touching an.
Okay, guys, there's no potential difference between inside and outside, but there's a huge potential difference between inside and outside of the metal of the car, but there's a huge potential difference between inside and the ground. All right, so if you're touching the car and you're touching the car here, the foot is still, one foot is still inside, you're touching the outside, the ground, there's a huge potential difference. The car is charged, the ground is not.
Energized object like a car while simultaneously touching.
Okay, so when there's a potential difference, what happens, the charges flow from high voltage towards the low voltage, and then the charges will flow through your body, which that's what it means. Potential difference means the charges will go through your body.
The ground.
The larger the voltage difference is, the larger the number of charges going through your body will be.
Electricity flows from the vehicle.
So the number of charges flowing through your body is known as
Through
electricity.
the body and into the ground, essentially making me into a human jumper cable, which would be bad. I gotta jump.
So the larger the voltage potential difference is, the more charges will have to go through your body to get to the ground. So the charges will always move from high voltage towards the low voltage. Like the objects are going to fall from higher altitude towards the lower altitude.
And land with both feet together.
Okay, notice that there's no potential difference between inside and outside of the vehicle. So which means that despite the fact that the vehicle is energized, you can touch the outside of the car, you're just fine. Because the inside and outside are at the same voltage or potential. So the car is an equal potential in essence. All right, so the best thing to do is jump away. Okay, so you cannot touch the car and the ground at the same time. And then once you jump, you have to keep your feet together. Okay, so if you want to know why, here's the reason why. All right, when you start to step away from the car, the further away you get, the smaller the voltage is going to become. Okay, so if the contact points are not at the same voltage or potential, if there's a voltage difference between your contact points, there's going to be electric field from high voltage towards the low voltage, which means that the charges will still have to travel through your body. All right, so which means that you have to keep the separation distance as small as possible. Smaller the separation distance is between 2 points of contact, the smaller the voltage difference is going to be. So the current is still going to go through your body. Guys, the ground is also energized. The current is still going to go through your body because the separation distance is so small between the contact points. The amount of current going through your body is going to be unnoticeably small. You won't, you will not feel it. All right, so next point is how you walk under circumstances. If you have to walk, keep your step size extremely close, because your feet are not going to be at the same voltage points, equal potentials. All right, one foot is going to be at a different equal potential than the other one. All right, so just keep the distance as small as possible. There are two things you could do: either hop or you have to shuffle.
Now, step potential.
You cannot walk away from a car like this. You cannot walk towards a car like that if there's a power line on that car. Just remember that. You can get yourself killed. That you cannot do. Okay, so there's just too much of a gap between you got too much of a gap between the contact points. All right, so this is called the step potential. Larger the distance between the contact points is, remember, that's the separation distance between two equal potentials. Larger the contact points is, the larger the separation distance times the strength of the electric field from high voltage towards low voltage is going to give the potential difference. More electricity is going to flow
Ground
through
is energized. Electrical current can travel through me if my feet aren't close together.
All right, so keep the separation distance as close as
Electrical
possible.
current enters through one foot and out.
This is closer to the car, so it's going to be higher voltage than this one is. So the charges are going to go from higher voltage towards the lower voltage. All right, so the larger the separation distance is, the more current is going to go through your body.
The further apart my feet are, the greater my chances of getting shocked. So I must move away using short, shuffling steps.
Shuffle, shuffle, shuffle. There you go. You got this, Steven. No large steps. Just keep on shuffling. Every day I'm shuffling.
I'm sorry, I can't come to the phone right now.
I'm busy trying to stay alive at the moment. Almost there. Hi, honey. No, everything's okay. No, nobody got hurt today. Well, except the, remember how we were talking about getting me a new car?
This was a little bit cheesy, but it's well done. Oh yeah, so here's a different variation of the same thing.
Sometimes power lines stay safely out of our way, but sometimes storms or accidents can knock down lines. If a power line falls across your car, do you know what to do? If your car is still drivable,
Okay, guys, one of the things that you could do is just keep driving if you can. There's no reason for you to stop.
simply pull out from under the wire. If your car is disabled, the most important thing to do is to stay inside. Use your
There's absolutely no reason for your car to become
cell
disabled.
phone to call for help. Keep others away from the car. Only get out when utility workers tell you it's safe. Never touch the car and the ground at the same time. The only time you should get out is if there's imminent danger, like fire. Open the door fully. Do not step out.
All right, once again, they do a really good job. All right, so you can touch the outside of the metal, you're going to be
Stand on
fine.
the metal framing of the car.
You can touch the metal inside, you can touch the metal outside.
Keep your hands close to your body to avoid touching the car and the
All right, and you can climb over the car if you wanted to. Oh, it's electrified, nothing's going to happen to you because it's an equal potential surface. The entire car is an equal potential. There's no potential difference between inside and outside. All right, but you cannot touch the ground and the car at the same time. Okay, and then you have to
ground
hop.
at the same time.
Okay. Now, it's something that I need to mention. Okay, so this is good. Keep the feet together.
Hop off with both feet. Hop away from the car.
Okay, if you fall, you got problems. Okay, the falling is one of the worst things that you could do right now because the top of your body is going to be at a different potential than the bottom of your body. Okay, you will get zapped. It could potentially kill you. All right, so this is not a kidding matter. Keep your feet together. All right, make sure that there's no spacing between your contact points because both feet, your contact points will not be at the same voltage or potential. So you have to keep the potential difference as small as possible.
Keeping your feet together.
All right, so the car becomes the source of the energy. So as you start to move away from the car, you have these different equal potential lines. So the voltage is going to diminish in this direction. So if you step outside, you will go, one foot is going to be at a higher voltage than the other one. So which means that you're going to end up getting zapped.
At a safe distance, slowly spread your feet apart. If you feel a tingle, put your feet back together and hop.
This is not bad. All right, so if you feel tingling, which means that it's not safe to walk. So just get your feet together, keep hopping around or shuffle.
For EMC TV, this is Greg.
This is really well done. All right, so what is it that we have to do? Okay, so we discussed that. Let's finish up the next page. All right, so this is done. Okay, so sparks occurring at a certain distance. The spark is going to occur only if charges have enough energy to jump the gap, right? So, which means that the oppositely charged regions will have enough energy to cause a discharge. So that's the reason why it usually happens at a certain distance. Okay, so whenever the gap is exactly the right distance, that's when if they have enough energy, they will jump. They won't be able to jump if the distance is larger. If it's smaller than that, then obviously by the time this distance gets any shorter, the discharge already happened. Which means that the charges will have enough energy to jump the gap at a certain distance. All right, so it's recommended that the people avoid high grounds during thunderstorms. Here's the reason why: because they normally, assuming that there's a uniform charge distribution, more than likely the charge will they will have enough energy to jump to the high ground sooner than the low ground. All right, so which means that the charges from the clouds and the ground will have enough energy to discharge at shorter distances than the larger distances. Next question is, if taller objects and structures are more likely to be struck by lightning, why then the CSR is not the one that gets struck lightning by 100% of the time? The reason is because the charge distribution is not uniform. All right, sometimes the charge distribution tends to be stronger when between two opposite charge regions which are further apart. It's just because it's a non-uniform charge distribution. It's a bit of a random phenomenon. Okay, so the last one is the one that we just discussed. So if there's a down power line touching the metal of a car, so the question is it possible to touch the outside of the vehicle without getting electrocuted if you're a passenger inside the vehicle? Yeah, because there's no potential difference between inside and outside of the car. The entire car is an equal potential. If there's no potential difference, then there's no reason for you to get shocked. You cannot get shocked because the electric field points in the direction of the diminishing potential. All right, if there's no change in potential between inside and outside of the vehicle, and there's none because there's no electric field inside the vehicle, because then there's no net charge inside the vehicle, there's no reason for you to get shocked, because lack of electric field means that there's nothing forcing the charges to go through your body trying to get to a region of lower potential. Okay, it's a really nerdy way of saying it, but that's what it means. No potential difference means there's no electric field within that region. If there's no electric field within inside and outside of the car, then there's no absolutely, you cannot possibly get shocked. All right, so that's the meaning of it. All right, so we are done with this chapter. All right, so I'll edit this and then put it online tomorrow, not tonight. Okay, so we're done.